Okay, hello everyone. We are moving on to chapter 9, normal subgroups and factor groups. This video will just focus on normal subgroups, and when we get to class, we'll talk about factor groups. Okay, so again, if you want to pause the video and write things down and then come back, that would be fine. Okay, so here in this section, we're talking about sort of a different, well, factor groups is going to be a different type of group because we're used to talking about like cyclic groups and permutation groups, and factor groups is another type of group. But normal subgroups, definition, so a subgroup H of a group G is called a normal subgroup of G. Okay, a normal subgroup of G if AH equals HA for all A and G. So in other words, the left coset equals the right coset, right? And we know that doesn't have to be the case, okay? But when that happens, we call that subgroup a normal subgroup. And the notation for a normal subgroup is sort of like this, it's like a little right triangle maybe, pointing towards the H, okay? And so something that you want to keep in mind, if a subgroup, if a subgroup is normal, we're not assuming that AH equals HA, okay? So we're not assuming that, but what we are assuming is that for some, if there's a little h and big H, and for all A and G, then what we assume is that when we take the left coset, AH, not coset, but when we take A composed with H, some element in H, right? It's going to equal some H1. It doesn't have to be that same element. Okay, it doesn't have to be the same element, and we'll look at an example so you know what I mean. Composed with A. All right, or if we're looking at the right coset, the right elements, then it could equal AH2. Okay, and so again, I think an example will help if that's not clear. Okay, so just some examples. One, for group G, the identity element is a normal subgroup of G. Okay, and that's kind of clear, right? Because we know the identity element, by definition, is going to commute, right? And so that means that the left cosets will equal the right cosets when you take E and compose it. And G is a normal subgroup of itself. Okay. The second example, just sort of stating it, if G is a billion, then every subgroup H of G is a normal subgroup, right? And that sort of makes sense because, again, it's sort of what this is saying. It's sort of looking like the abelian property, right? But the thing to keep in mind is this note right here, because we're not saying that every element, we're not saying that whatever H is, AH is going to be the same as HA. We're not saying that. But if it's a billion, okay, if G is a billion, then every subgroup H of G is a normal subgroup. Okay. And example 3. So let's look at this. So let H equal A3. Okay, so that, remember, that's the alternating series. So that's our even permutations. So that's E 1, 2, 3 and 1, 3, 2, right? Because we have even number transpositions, right? That is a normal subgroup of S3 under composition of functions. Okay. Okay. And that means, so any A for all A belonging to S3, A times A3 is going to equal A3A, right? Again, we're not assuming, and I'm going to show you so you can see what I mean about you're not assuming sort of that abelian property that AH equals HA, okay? So let's look. So if, let's say A is 1, 3, right? Then let's take the left. Let's start with the left coset. So 1, 3, A3 will equal, well, that's 1, 3, E. And then that's 1, 3, 1, 2, 3. And 1, 3, 1, 3, 2, right? And so if you compose those, and you can sort of pause for a minute and compose those to make sure you get what we're going to get below. Well, that we know that first element is going to be 1, 3. If you do that composition, it's going to give you 1, 2, and that's going to give you 2, 3. Okay. And so if we take now the right coset, that's not the eraser, there we go. Okay, so then that is E13, comma, 1, 2, 3, 1, 3, comma, 1, 3, 2, 1, 3. And this will equal 1, 3, 2, 3. Oh, that was loud. I don't know. My computer is going through some issues. And then 1, 2. Okay, so notice that the left coset equals the right coset. However, I want to note that if we look at this 1, 3 and 1, 2, 3, let's for instance, we see that that's 1, 1, 3 and 1, 2, 3. We see that gives us 1, 2, right? But if we look at 1, 2, 3 and 1, 3, then we're going to get 2, 3. So that's what I mean. They're not equal. However, what we are saying, because it's a normal subgroup, we are saying that there is an element in, so here we're looking at the left coset, right? So there is an element in the right coset that's going to, so there's an element on the right coset that will equal 1, 2. That's what we're saying in terms of it being normal. And that element is what? 1, 3, 2. Okay. And so in terms of what we were talking about, we can look at this. I'll do this. So if this is our A and this is our H, we're saying that we could say H prime times A that is equal to. Okay. I hope that made sense and made the definition a lot clearer. Okay, so just continue with some examples so you can think about this whole normal notion. H equal, if H was E and 1, 2, this is not a normal subgroup. Of S3. And I want you to try to figure this out and tell me in class, why isn't it? Why is it not? And this may be worth an extra credit point back on the exam. So when we get to class, if you can tell me why that is not by showing an example of why it wouldn't be, we shall see about the extra credit. All right. And then, excuse me, H, where we have E, which is R naught, R1, R2, R3, which this represents the rotation of a square. So we haven't talked about that in a while, but remember we first started talking about groups, we sort of looked at it from those rotations of, I think we had a triangle, but I believe we also talked about a square. Normal subgroup of D4. Okay, and so if you want to try that out and practice with that, that'll be good. Okay, so there are two proofs that I want to do. I think I'm gonna finish the video with this proof, and then we'll do a new video for the next one. I don't like going over 15 minutes. Okay, so normal subgroup test. So you can use, of course, the definition in regards to showing that a group is normal, a subgroup is normal, but also we have this theorem that says a subgroup H of G is normal if and only if X inverse is a subset of H. Okay, and you can sort of see what's going on here, because with this, if you looked at that and did X on the right on both sides, you'll have that XH is a subset of HX, right? And so that gives us the definition. So this is another way to define a normal subgroup. Okay, and I think there are a couple other ways too. You might, if you're reading other books, you might notice. All right, so let's prove this. First, going the forward way, the direct way, suppose H is a subgroup of G and that H is a normal subgroup of G. Okay, so here we want to show that X, H, X inverse is a subset of H. Okay. So since we're assuming it's normal, that means for all X and G and for all H and H, there exists an H prime in H such that XH equals H prime X, right? And that goes back to because we can't assume that XH is going to be equal to HX, okay? Well, thus, if that's true, then X inverse equals H prime, which means that X inverse is a subset of H, right? Because again, we said for all X and G, for all H and G and H, this will happen, which leads to this, which leads to that, which means every element here is in here. Okay. Now, proving it the other way. So now we're supposing XH, X inverse is a subset of H. And I'm going to call this star because later in my proof I refer back to it as star. Show that H is a normal subgroup, all right, which means we need to show that XH is equal to HX for all X and G. Okay, so just using the definition. All right, well, so if we multiply the right side of that by X, we can say that XH is a subset of HX. And since star is true for all elements, then we can take X inverse, because X inverse we know is going to be in G. So X inverse H of X inverse is a subset of H. Okay. So if we simplify that, that's X inverse H X is a subset of H, which implies that HX is a subset of XH. Okay, and so now we just shown that that XH is a subset of HX and HX is a subset of XH. Therefore, since we showed they're subsets of each other, XH is equal to HX, and therefore H is a normal subgroup. All right, we will stop this video and start a new one. It's not going to be too long to finish up one more theorem.